Earlier in the year, we learned how to draw trigonometric graphs in degrees. So now that we're drawing them in radians, you might think it's just a straightforward matter of switching the names of the degrees into radians. And it is. If you know how to draw a graph in degrees, you can go ahead and do it in radians. Make sure you know that 2 pi is 360 and away you go. But let's examine first why we'd want to do this. There's a really good reason for it, other than just the fact that we're trying to work in radians now. Let's think for a second, we'll go back, about what a radian really is and why it doesn't have units. If I take some angle, let's call it theta, and look at what theta really is in size, how do I measure it? Well, in radians we say it's the length of this arc, let's call that L, over the radius, let's call that R. So it's actually a ratio, and that's why it doesn't have units in it. We don't need to write that's this many radians, because it's a ratio between the lengths of things. If we look at what the sine of theta was, though, on that exact same diagram, we'd have to draw a line down here, drop a right angle line down to meet the other line. This is also a radius, don't forget. And now the sine of theta, this angle here, would be the opposite side, let's call it just O for opposite, over the radius. So again, the sine of the angle is a ratio between two different lengths. But the angle itself is also a ratio between two different lengths. So it makes sense that these both have no units in them because they're ratios, but they can talk to each other because they're inherently related. So one thing that you're going to notice then is that for a lot of our course, we're talking about calculus, differentiating. We're always finding dy dx, aren't we? And looking at what the gradient of a curve is. Well, if you were to look at what the gradient of a curve was and you'd graphed it using our old method, with 360, 180, numbers of degrees here, then if you had your scale right, if this is 360 of something and your sine graph only goes between 1 and -1, the scale would have it such that it would be a line that looked almost flat. You'd barely see the wobble in it. So it really wouldn't be relevant, and especially given that degrees are so arbitrary. I mean, why 90 degrees in a right angle? Why not 50 or 100 or 20? This makes far more sense and it allows us to differentiate. Let me explain. If we have one here and one here, then when you're drawing your graph, first thing you should do, work out how tall you want to make it, put your ones in if you're graphing y equals sine x, and then what I do is I think, well, if that's 1, I do this even without a ruler, and you can do it quickly. If that's 1, then I'd have 1, 2, and I make this around about 3, maybe 3 and a bit. But if it's sort of 3-ish, it's looking about right, isn't it? And then I put, I'll say that will be pi, because pi is about 3. Then I can put 2 pi, make it twice as big, and then I put a line in between for the halves, and then away I go and I can rough in my sketch of y equals sine x. Now what you're going to notice straight away is that now that the scale is actually meaningful, this is 1, but this is also 1. So I can now actually have a look at the gradient of the curve in any one place, and it's going to mean something. What does it actually mean? So let's now have a go at drawing the gradient function for this curve, y equals sine x, and we'll put it on the same axis and you'll see something cool. What would you guess the gradient is right here? I'm thinking this looks like a 45-degree angle, and in fact it should be. We'll learn that later. This looks like a gradient of 1. So if I use red pen here, and I say at that point the gradient's 1, I'm graphing the gradient in red. What about over here? What's the gradient at this turning point? Well, it's flat there, isn't it? So that's a gradient of 0. So at that point, when x is pi over 2, the gradient would be 0. What about down here? We've got a gradient of -1. So I'd graph that down here. A gradient of 0 again, and a gradient of 1 again. You can see that there's a pattern. Now, the way it turns out is that this is the gradient function of y equals sine of x, and what I've actually just drawn, you might have guessed it, is I've drawn the graph y equals cos of x. So it's quite cool that if you differentiate this graph, what you get is this graph. And we'll see a lot more of that when we investigate trigonometry again in Year 12.